Welcome back, everyone. This is the fifth video in this Wi-Fi 6 series. We are still in the file layer enhancements section. Today, we will wrap up this section and complete the discussion of the remaining enhancements. So let's begin with MuMiMO. So MuMiMO stands for multi-user, multiple inputs, multiple outputs. The MU part of the term is easy to understand. It refers to having a group of users that are trying to communicate with the access point at the same time, or vice versa, meaning the access point is trying to communicate with these users at the same time. But what is MIMO? So MIMO, as per the book definition, it is a sophisticated form of antenna diversity. Okay, so someone might say, I didn't understand the first term. Now you're giving another term. Don't worry, and let's define diversity. So diversity refers to the usage of two or more antennas in order to improve the quality of signal in transmission or reception. So now let's get back to MIMO. MIMO, based on the definition of diversity, can be defined as a radio architecture that transmit or receive using multiple concurrent antennas at the same time. Okay, so MIMO actually exists since the days of 802.11n. It was actually used prior 11an it was used in order to reduce the effect of multipath. And basically, what is multipath? I might have an access point here, hang to the ceiling. Let's assume this is a room, a big room, and I have an object here. And let's say I have this user with a mobile device. We have an object that is covering the access point. So by using multiple antennas here, okay, and at the same time, by using multiple antennas at the mobile device, we might have the first, let's say, transmission from the first antenna going going to the object, getting reflected, and then let's assume it reaches the device. At the same time, there is another one reflected. Maybe this antenna gets to the user like this, maybe gets to the user like this. So this is just as an assumption. The idea is the usage of multiple antennas at the receiver will be used in order to extract the best out of all received duplicated signals. There is something I read long time ago. As I remember, it is antenna or switched diversity. It relies on DSP, okay, digital signal processing techniques, in order to extract the best signal out of all, let's say, received versions. And it will also select the antenna that received the best signal in order to reply back to the access point. Okay, so you don't have to focus on this. This is just as, let's say, FYI information for you. The idea is MIMO was used prior 11an to reduce the effect of multipath in indoor environments. Okay, now it was officially introduced as a term or a new enhancement in 11n at the file layer. Okay, let's clear things. Now, also in 11AC, MIMO continued to be there, and the concept of MuMiMO started there. So the difference between MuMiMO in 11AC and 11AX are the following. Now, in 11AC, we used to support, let's say, 4 antenna elements, okay, which means 4 MIMO antennas. If we use 1 antenna per user, then we would be able to support 4 STAs or to transmit to 4 STAs at the same time. In 11AC, or sorry, 11AX, we are using 8 antenna elements. So the same assumption, if we are using 1 antenna element or one spatial stream, because antenna element would refer to having 1 spatial stream, then we could support, let's say, 8 stations. Now, actually, depending on the station capability, let's say I have a super high-end laptop with 3 by 3 and 3, which means the laptop is capable of having 3 transmitters, 3 receivers, and capable of receiving 3 concurrent spatial transmissions at the same time. Then let's say using 11AX, I can assign 3 antenna elements to serve this user, while I have 2 mobile devices. Each one has 1 antenna or capable of receiving 1 spatial stream. So I might assign 1 antenna element here and another antenna element for that. Okay, that's good. So we have this difference, but in 11AC, we had a drawback at that time. So let's imagine it like this. Before we draw, the drawback actually in 11AC, it was related to forming stations group. So basically, let's say I have an access point. It is mounted in the ceiling. I have our client here. I have a client here, and I have another client here. These clients are within the cell of the access point, okay? And for the access point to be able to communicate to these clients at the same time, it has to establish a station group in order to direct or beam the transmission to those users. In 11AC, there was a lot of problems forming this station group because actually 11AC introduced, I don't remember exactly, they call it sounding techniques in order to understand the dimensionality of the channel, and it tried to steer, let's say, the certain transmission to each user by itself. Now, in order to do that, it has to actually create a station group. Now, there was a lot of hurdles in creating that, but let's, roughly speaking, assume that the access point succeeds in creating this group, and let's assume it is actually transmitting. Another problem arises, which is if this station moved from this location, let's say, to another location, let's say here, okay, it is still within the coverage cell. Now, the access point has to reform the group. So for this, the synopsis about continuing to use this downlink multi-user transmission is to have the stations in steady state, meaning they are not roaming or they are not moving around the facility. Now, in 11AC, in 11AX, the latest standard introduced the trigger frame, in which actually a specialized frame, as we have discussed. It includes a lot of information related to a triggering multi-user transmission, whether in the uplink or in the downlink. It, as we have seen, it simply contains information like number of spatial streams used per user, and we can imagine that the number of spatial streams can be represented or assigned to, let's say, antenna elements, and assign those to communicate with those clients directly. So OFDMA has, or sorry, 11AC had this problem. 11AX resolved it by introducing a new frame type that could be used to arrange the trigger of the transmission. Okay, good. Now we have discussed, let me clear things. We have discussed about MIMO, which is a multi-user technology, which uses the antennas to communicate to multiple users. And we have OFDMA. It's also a multi-user technology. It was imported or borrowed from cellular world, as we have discussed. This one subdivide the channel into chunks and assign each chunk to a user and allow them to transmit or receive concurrently. So both are multi-user technologies, but now in a wireless cell, when you build your Wi-Fi network, which one is better to use? The short answer is let's have a bit of both, or both of them used within the cell. Why? Because in a cell, okay, we might have mobile devices that are running bandwidth greedy applications, whereas another mobile device runs, let's say, a let's say VoIP application or real-time applications which actually requires less delays and jitters, etc. So now, based on the traffic type, I can use the technology that was designed for that. So based on traffic type, we can consider both technologies complementary to one another. Why? Because multi-user MIMO is designed to increase the network capacity. So it is more suited to bandwidth greedy applications such as video or video streaming. Whereas the OFDMA is used to cut actually the MAC layer overhead, thus reducing the latency and jitters. So it will be more suited to real-time traffic or traffic that has smaller frame types. Compared to videos actually have bigger frame sizes. Okay, so this is a quick comparison I added for your reference. This is targeting high efficiency. This is targeting high capacity. This will reduce latency. This will increase data rates because we have multiple antennas that are sending different data streams. So that will accumulate data, thus increasing the data rates. This will be suited for low bandwidth applications, while this for high bandwidth application. This is with a small packet size, whereas this with higher or larger packet size. Good. Now, both technologies, as we have said, are multi-user technologies. So the AP, as we have discussed previously on or about Mu-MiMO, the AP scheduler takes care of assigning the frequency resources on per frame basis. OFDMA will be actually also a function of the access point itself. So since the access point acts as a central controller for all MU operation, then it will actually resemble the base station or enhanced node B or next generation node B in cellular world. By the way, this is used in 3G network, this is in 4G or LTE, and this is in 5G. We have already mentioned that. Good. Let's clear things. Let's move to the next section. Okay, good. Now, we are going to show how these multi-user technologies work together by plotting over a time, frequency axis, and spatial axis. Before that, the time axis refers to the time domain, okay? Time domain. The frequency axis refers to frequency domain. Spatial axis refers to spatial domain. Now, the time domain, the changes will be done in the time axis. If I change anything on the frequency, then changes will be applied to the frequency domain, which would refer to the channel that the access point uses. Now, this is new. It is the spatial domain. So we said that the access point will have multiple antennas, let's say 4. So each or any access point that has multiple antennas can actually segment the transmission in spatial domain. So I can use this for to direct or steer transmission to user 1 that is spatially distinct from user 2 and so on. Okay? So the key takeaway here, if I'm using multiple antennas to perform the change or the transmission, then I'm doing, let's say, kind of segmentation on spatial domain. Whereas if I am subdividing the channel, then I'm using the frequency domain division, and time is something will be shared by everyone. Okay, now let's take this scenario. We have a wireless cell. We have 4 devices associated or connected to this access point. Each one is denoted by a color. So now we will start usually by a single user transmission. Let's see first how a single user transmission, let's say, plotted over these axes. By the way, before I do it, I have this axis. So this is Y, this is X, and this is Z. So this is time, frequency, and this is spatial. This plot here would refer to the same axis that we have included here, but it was revolved. And the Z, or the spatial domain, it should be here, but I have shifted that to this location because putting that here would hide what I'm going to show. Good. Now let's start with a single user transmission. So I will go a little bit slower in explaining. So we have user 1. Now this one will be given the time to transmit, but at the same time it will actually use or reserve all the frequencies within the channel, and at the same time the access point antennas, all of them will be used to beam or steer the transmission toward the client. After the transmission ends, it's time for client 2, same thing, client 3, and after that client 4. So in single user MIMO, you would expect this to be sequential transmission. I reserve the channel, regardless if I'm going to use all frequency resources within that channel or not. I will reserve it. and I will take that X amount of time to transmit. Once I finish, the resources will be freed, the next user would come. Good. Now, let's move to OFDMA. So, in OFDMA, let's recall together, OFDMA is a multi-user technology that operates in frequency domain. So, any changes, let's say, would be expected to be within the frequency axis. Let's just see how the transmission would be, and we can explain. So now I have all users. The AP scheduler will decide which, let's say, RU to be assigned to which user. So, okay, by the way, everything will be assigned and at the same time, and all users will be using the frequency resources within the channel at the same time, whether it is uplink or downlink transmission. The idea is time is still shared between all of these users. As you can see, it's shared, whereas frequency changes or differs between one user to another. Okay, this user will use this part of the frequency, this user will be using this part, etc. In terms of spatial domains, I don't know, but I think all antennas will be used to steer the same transmissions to all. This is as per my understanding. Okay, so this is the OFDMA transmission. Then everyone would leave the channel either at the same time or on different times based on the transmission time assigned for each one. Now let's go to multi-user MIMO. Same case, same cell, same number of users, but a MuMiMo will actually work or exist in spatial domain. So we would expect a change in the transmission in the spatial axis. Let's see. So we will have the users actually using the channel all at the same time, okay? And they will use the same frequency resources, okay? But we will have, oh, sorry, let me get back, grab the pen. We will have, let's say this is antenna 4, this is antenna 2, this is antenna 4, 3, 2, 1. So each one will be using or will get its transmission from separate antenna. So this is how the transmission occurs in multi-user MIMO operation. And if you remember, we said that it's always better to combine both words. So let's see how a OFDMA and MuMiMo transmission would look like if we combine them within the cell. So now since we combine both of them, time will be shared actually between all users at the same time, but we might have two users using separate let's say frequency channels, let's say RU1, RU2, but they will be using, for example, let's say antenna 1 and antenna 2 to communicate directly with both of users, whereas also this user and this user would be using RU1 and RU2, but we have separate antenna elements communicating to both of them. By the way, I just put it in this way just to show an example. You might have this moved on top of this and this moved on top of this. So each one is using a different RU and different antenna elements. Okay, so that's all I have about the multi-users technology. Let's recap on high level. Both of them are multi-user technologies. Each one is more suited to a certain traffic type. So OFDMA is for real-time jitter and latency sensitive traffic, whereas this is more suited for high bandwidth applications, let's say videos or larger file transfer, etc. Okay, now let's clear things and move to the other section. Okay, now the last enhancement that we will discuss in the file layer is the usage of 1024 QAM. Okay, let's bring things and discuss it. So basically, the usage of this modulation allows us to do the following. So this number is 1024, can be actually represented as 2 to the power 10. 10 refers to allowing 10 bits, okay, to be used inside a Wi-Fi symbol. Now this is in 11AX. In 11AC, which used 256 QAM, okay, 256 equal to 2 to the power 8, okay, so 8 allows us to include 8 bits inside a Wi-Fi symbol. So which one is better? There is no brainer here. For sure, 1024 QAM is better because within the same Wi-Fi symbol that I use to transmit or transfer at the 11AC days, I can use the same symbol, but let's say add more bits to that, so that would actually increase the efficiency of the transmission. Good. So the second enhancement by using this modulation is that 11AX introduced an optional modulation type. It's called dual carrier modulation, or DCM. This one is used to enhance the transmission robustness. How? Let me explain it. Let's say I have, let's say, an access point, okay, and it wants to transmit data, let's say, to user, okay. So what it does is that it can, and let's assume before that I have this user assigned RU1 of 26 subscribers, okay, 26 subscribers. Not subscribers, I meant subcarriers, sorry. So now using DCM, the access point does the following. It transmits the same signal on a tune, okay, which is something inside the RU. And in order to increase the robustness of transfer, it will actually transmit the same signal on another tune. So instead of using one tune, I can use both, two tunes. That would help the receiver to, for example, extract the original transmission or the original signal, given that one of them got corrupted during the transmission, using for sure DSP or digital signal processing techniques. Now, this is good because it allows better error recovery, but at the same time, it reduces the data rate twice, because instead of using the other tune to send other, let's say, data or signals, it will perform duplication. So that actually reduces the bandwidth, or sorry, the data rates by 2. So 11AX allows the usage of this modulation only at the lower MCS data rate values. Okay. On the other hand, doing that would enhance or would provide 2 dB gain at the receiver. Okay, so um, this is good. And now just let's have a look at the constellation diagram. So you can see from the differences between 11AX and 11AC how denser the constellation diagram becomes compared to 11AC just by adding 2 bits inside the symbol. And now uh, it is mentioned here that it provides 25% of higher capacity. I don't want you to memorize that. It's easy. The change that we have here is 10 bits, whereas here, 10 bits, whereas this is 8 bits. So if you just divide both of them, we would result or the number would be 1.125. So 1 can be removed by removing the 8. So the remaining is 25, which refers to the percentage of capacity enhancement that we have at this point. Okay, good. So I think we have finalized all the physical layer enhancements that we intended to discuss. In the next sections, we will actually start with the enhancements that 11AX introduced in the at the Mac layer. In my opinion, the 11 AX5 enhancements are easier to understand compared to the ones in the Mac layer. So we will discuss everything in details, don't worry. For now, I hope you find everything useful. I know I took longer and I moved or I got into the tiny details to explain things, but I just want to make sure that you get it in the right way. And at the same time, if I don't understand something, I would appreciate that you write for me and let me know if I explained anything incorrectly. We can learn from one another. Okay, good. Let's stop here. Let me clear things and see you in the next section. Thank you for watching.